You may not get to see an eruption very often, but we live on a volcanic planet where they happen all the time. Most volcanic activity happens not on land, but kilometres underwater in the deep ocean, covering 2/3 of the Earth's surface.
Whoa! Holy moly!
This is a story about volcanic hot springs called hydrothermal vents.
Passing 1600 meters, over.
Told by two explorers from different scientific viewpoints. One, a geologist.
There's ones who like dinosaurs and ones who like volcanoes, and I'm one of the volcano-loving ones, so it's great for me.
And the other, a biologist.
The roots of the tree of life, as we know it right now, the deepest roots we know of, come from hot springs.
And both have undertaken research on deep-sea vents for a company with a daring plan to mine them. In 1990, Cindy Lee Vandover became the first woman to pilot the US submersible Alvin. Routinely diving to depths greater than 2,000 metres, she's explored nearly all of the world's known hydrothermal vent fields. Chains of them occur along fault lines, like the Pacific Rim of Fire and the Mid-Atlantic Ridge.
Even after 100 dives like I've made, there's a sense of anticipation, of not knowing what you're going to see when the floodlights come on.
Here's how hydrothermal vents work. Under incredible pressure, seawater pushes into fractures, is rapidly heated, picks up chemicals as it reacts with the hot rock, and gushes out of the seafloor at scalding temperatures. What was once plain seawater is now hydrothermal vent fluid.
What's special about these environments is that it's this wonderful mixture of vent fluid and cold seawater with chemicals that microbes can use to make new organic materials. So it sets up a food web. And once you have that food web set up, then species can come in and use it.
This dark, toxic, unstable environment supports an amazing array of bacteria, snails, mussels, and crabs. In the eastern Pacific, giant tube worms grow to 2 metres in just a couple of years.
They have no mouth. They have no gut. How do they make a living? This is a giant animal on the seafloor. Where is it getting its nutrition? And the answer is that they have bacteria that live inside of them.
With their symbiotic microbes, the animals crowding around deep-sea vents aren't the only ones seeking out plumes of sulfide minerals. So do geologists.
That's a really, really nice black smoker. And that's about as black as you get.
How big would something like this be?
Oh, that's probably 1.5 to 2 metres in height.
But they come a lot bigger than that.
It's enormous. That's absolutely enormous.
That's Chris Yates you can hear in a submersible at a depth of more than 1,600 metres, exploring a vent field and collecting samples of chimneys like this one.
This central cavity here would have been full of very hot water. You're talking about stuff which is 250 or 300 degrees centigrade. And pumping very rapidly. It may well have been a black smoker with black smoke coming out of the top of it. And you sort of had a very sharp temperature gradient between 300 degrees here and 3 degrees out here.
As the hot, acidic, chemical-laden fluid hits the cold seawater, the metal sulfides drop out of solution to grow a chimney, or when the fluids are really hot, to form a huge plume of particles that looks like black smoke.
You come on a black smoker and it's like being in an industrial landscape. They can be really quite tall structures in some places, 30 meters tall.
You're sitting on the side of an active volcano, there's constant earthquakes. These structures are quite fragile. They're constantly changing and evolving, collapsing, starting, finishing.
To biologists, the discovery of more than 500 previously unknown species living on deep-sea vents makes them cradles of biodiversity.
I could take you tomorrow to a place where we would find a new hydrothermal vent that would almost certainly have dozens, if not hundreds, of new species.
To geologists, vent fields are the birthplace of giant ore bodies with grades of copper and zinc many times higher than those found on land. And that's got the attention of mining companies.
This is the Big Pearl chimney. It's the biggest chimney ever dredged from the seafloor, and I'm sitting down near the base here, and the fluid would have been gushing up from the bottom towards the top.
So it's extinct now, that's why it's all filled in, but it's full of minerals like gold, silver, zinc. Is it worth mining?
Oh, certainly worth mining.
This chimney comes from a vast hydrothermal vent field deep in the volcanically active Bismarck Sea of Papua New Guinea. And it's here that a company called Nautilus Minerals is planning Solwara 1, the world's first open-cut mine for copper and gold on the seafloor.
The amount of metal value you gain from mining something like Solwara 1 is the kind of metal you gain from mining something 10 or 15 times the size on land. So potentially they're a very efficient way of mining.
Here's the plan. On the seafloor at 1.6 kilometres deep, 3 remote-controlled robotic miners crush the chimneys and grind up the sulphide deposits, which along with everything living on them are sucked up by a giant vacuum cleaner to a ship on the surface. The slurry is filtered and the waste sent back down the pipe to the seabed where it's released. Over a period of 18 months, 2 million tonnes of ore would be mined from the vent field and shipped to nearby Rabaul. During the time I was making this story, Nautilus Minerals declined my invitation for an interview and announced a joint venture with the PNG government to start mining within the next few years.
The activities that Nautilus are proposing are something like ploughing a field or raking your garden, that you're stirring up the environment, but you're not fundamentally changing it.
We don't know, when you scrape away 5,000 years of deposit, what influence did that 5,000 years of deposit have on the fluid chemistry and the kinds of animals that might be able to colonize it? After
mining, it's likely that vent structures will reform and animals will recolonize. But the question is, how long does it take?
What interests us as scientists is that here's a question we just don't know the answer to. And if extraction of metals on the seabed takes place, we'd like to know what happens and how quickly the animals come back.
If Nautilus Minerals is successful, it could spark a gold rush of seafloor mining in international waters without knowing how to restore the habitats after mining.
There's nobody who's an expert in that. No expert exists right now who has any idea how to tackle that. I'd love to know that 100 years from now, people would look back and say, that's the generation that got it right.